Hey everyone, it's your main math teacher, Mr. Boyden, back at it again, and today we are doing optimization. This is an application of derivatives. We've got all of our derivative rules down, and so now we're going to look at one way that derivatives are useful sort of in the real world or in some sort of an application. Okay, and this one's called optimization. And so to start thinking about how we're going to do that, let's consider the two questions below. First of all, if I ask you to find a minimum value of a function, what would you do? Would you look at the function? Would you look at the derivative of the function or the second derivative? What would you do? I hope that you remember that if you're looking for a max or a min, extrema as we call them, you are going to look for critical points. And that means that you're going to be looking at f prime. And so we take f prime and we set that equal to 0, and then we know that's always going to give us our extrema. And so with that in mind, let's look at the next question below. This is sort of the guiding principle that's going to lead us throughout this lesson. So if you were asked to find the minimum value of 3x squared minus 6x plus 2, how would you do that? And I'm asking you to use your calculus brain. And the reason I say that is now that we've gone through pre-calculus, you can probably look at that and recognize that's a parabola that opens upward. It's something like this. And so its minimum value is right down there at the vertex. And you could probably figure out what the vertex is with some sort of a pre-calculus method. I don't want you to do that though. I want you to use your calculus brain. So remembering what we looked at up here, that we're looking for where f prime equals 0. Let's find f prime. Let's actually find the derivative and set it equal to 0 and see what we get. Okay, so taking a derivative, f prime, we get 6x minus 6. And remember that little 2 goes away because it's a constant. And we're setting that equal to 0. And we want to solve that. And when we do, we get x equals 1. And we were asked for the minimum value. When they say minimum value, what they really mean is the y value. That's the minimum y value. And so we're going to need to plug that back in. And so when we do, we get 3 times 1 squared, which is 3, minus 6 times 1, which is 6, and then plus 2. Looks like we've got 3 minus 6, so that's negative 3, plus 2 is negative 1. Okay, so we know how to find max and min values. And so what we're going to see today with optimization, optimization is just a way of using that exact same understanding to answer some potentially pretty meaningful questions. We're going to get into some of those meaningful questions in today's lesson. They're going to get a little more meaningful in the assignment we're going to have, and then we're going to do an activity in class in 2 days, and then we're going to see some really deep meaning of how optimization works. So let's get to some of our examples so we can build up a little bit of understanding. Here's our first one. Okay, we're going to do one that's not really an application, just a way of getting more comfortable with the idea of what we're doing. Product of two numbers, or of two positive integers, is 324. All right, let's pause and let's write that down in math. We've got a nice sentence, let's write it out mathematically. Product, that means multiplication. I'm going to call my two positive numbers, or my integers, x and y. Let me try again. My screen is not being very friendly today. You know my handwriting's not that good, but I swear it's better than that. So trying again, x times y equals 324. Okay, so that's the first part. We want the lowest possible value of the sum. Remember, that's addition of the two numbers. So x plus y. And going back to what we talked about a minute ago, we talked about maxes and mins. They said lowest possible, so that would be a minimum value. Hey, there's better handwriting. That looks better. For some reason over here, the computer thinks I'm writing a squiggly. I swear I'm not. I promise. All right, so we know that x plus y is going to be a min. And so that's why I asked you that question a minute ago. If you had to find a max or a min, how would you do it? You'd take a derivative, you'd set it equal to 0. So what we're going to want to do is we're going to want to take a derivative of this and set that equal to 0 and see what we get. There's an issue though. This equation has x, it has y, and it has a word in it. It has the word min, and equations aren't supposed to have the word min. Well, remember, I've been saying it all along this year. One of the things that we do in calculus is we take rules that we know and we break them because we understand math well enough to understand the consequences of breaking those rules. And that's exactly what we're doing here. So that's why I'm writing a word in there, min. I'm writing that in there as a placeholder because in a minute, when we take a derivative, what does a min look like on a derivative? It looks like 0, so that's going to turn into a 0. But before we do that, we have to get an equation in one variable. Right now we have x and y, and that's a problem. But that's what this equation over here is all about. We can actually solve this in such a way that we can get that y to go away. And so I'm going to divide both sides of this by x. And so those x's cancel out. And now I have y is 324 over x. And so we're going to make a nice little substitution over here now. So we get x plus y. I'm not going to write y. I'm going to write this, 324 over x. However, I'm going to write it in a way that is a little bit more calculusable. I'm going to write it like this. 324 x to the negative first equals a min. Okay, and now I can take a derivative of both sides. So let's do that. X is going to turn into 1. Let me get rid of that little dot that somehow appeared. So x turns into 1, and then when we take a derivative of this next chunk, remember the negative 1 is going to slide down and we're going to subtract, so we get minus 324x to the negative second power equals, don't write min. It's not a min anymore. Remember, this is now a derivative function. So min, when you take a derivative of a min, that's going to look like 0. Okay, and that's what that initial question was about. If you were asked for a min, how would you do it? And we needed to think about that in advance so we would know that that's why that's going to turn into 0. Now all we have to do is solve this out and we're going to have our answer. So let's do that. Maybe it makes more sense if we rewrite this as 1 minus 324 over x squared equals 0. Then, when I move this over here, it'll make a little bit more sense. Okay, so here we go. So I get 1 equals 324 over x squared. Let's multiply both sides by x squared, so the x squared comes up here. And now all I have to do is take a square root. And what is the square root of 324? Well, that would be 18. So x equals 18. Let's pause for a minute. Let's see if we've answered the question. So I'm going to scroll up again here, and let's see what the question asked for, see if we've answered it. They asked us, what is the lowest possible value of the sum of the two numbers? We've only found one of the numbers. So right now we know x is 18. So what I'm going to do is I'm going to come right back up here and I'm going to plug that in. So I get y equals 324 over 18. Turns out that's 18. And so we found that minimizing value. They asked, what is the minimum sum of those two numbers? That sum right there, well, we know that's 18, and that's 18. And so what do we get? We get our sum is 36. That is the minimum sum of the two numbers. Okay, let's try another one. This one we're actually getting into somewhat of a real application. So imagine we have 625 meters of fencing and we need to make some sort of a rectangular pen. Maybe we're holding in livestock or something, like something from my youth is something we do all the time. What is the largest area we can enclose given these particular conditions? So let's write out what we have in math. That's going to be a theme with this. We're going to take sentences and we're going to turn them into equations. So 625 feet of fencing material and we need a rectangular pen. Okay, rectangular pen, I have no idea what the dimensions are, but I know that this length is the same as that because it's a rectangle and this is the same as that because it's a rectangle. So I'm going to be fencing all the way around. That's 2 x's and 2 y's for a grand total of 625 meters. My area, I want that to be a max because they said largest area. So area, which is going to equal xy, I want to be a max. And so I have two equations, and that's pretty much how these are always going to go. We're going to get two equations, we're going to sub one into another, take a derivative, and solve. That's all it is. Okay, so I'm going to start with this equation up here. I want to try to simplify it because I can. So I'm going to divide both sides by 2, and I really like smaller numbers, so here I go. I get x plus y equals 312.5. That just got a little bit easier for me. Now I'm going to look back at the left, and my goal is I want to take a derivative of this equation so that that little max right there can turn into a 0. But there's a problem. I have x and y, and I don't know how to take a derivative when there's both x and y. So we need to make a substitution. Since everything we've learned so far has dealt with taking a derivative of x, let's see if we can get the y to go away. So the way I'm going to do that is I'm going to subtract this x over to the other side. And now I have something that I can plug in for y. And we're going to try that. So bringing that back over to the left, what we now have is we have x multiplied by y. Y is 312.5 minus x. And that equals a max. And so we can take a derivative of that as it's written if we want to. That's going to require a product rule and a cloud and a little bit of work. I think it's easier if we distribute the x, and I think you'll see why. 312.5 x minus x squared equals max. Now it's pretty easy to take a derivative, so let's do it. Derivatizing, I get 312.5 minus 2x equals 0. And that's going to be super, super easy to solve. When we do, we get 156.25 equals x. Now, it's always good when we get something that looks like it's an answer, like an x equals a number type answer like we have here. It's good to go back and read the question again, so let's do that. We were asked for the largest area. Okay, we can figure that out. That's no big deal. In order to find the area, which we have over here, we're going to need to know both x and y. And we already know y, so I'm going to come back up to this original equation, and notice this is the same exact steps from the first question. We found our answer, subbed it back in to answer the question. So I'm going to plug that in here. Y equals 312.5 minus x, and we just found x to be 156.25. And it turns out that we get 156.25 when we get that. And that's our y value. And now that we know both x and y, we can multiply them together. So we want x times y, which is 156.25 times itself, because x and y are the same, so square that. And what do we get when we do that? And I'm going to round this, it's going to be approximate, 24,414. Ooh, let's remember our units. What were our units in the beginning? They were meters. This is an area, so this is meters squared, or square meters. And that's our answer. Now let's dig into something that maybe is a little more useful. This is inspired by a paint can company, and paint cans, if you're a company selling paint cans, you want to make paint cans that are durable, but are also as cheap as possible, because the cheaper you can make a paint can, the cheaper you can sell the paint, or the more profit you can make. And so there's value in this. Same thing with boxes. We would want to optimize the amount of cardboard used in a shipping box, because you want your stuff to be shipped safely, but you also want it to be shipped cheaply so you can save money, or as a company, you can save money or make bigger profits. Let's dig into this one. Okay, we're going to produce a paint can that's going to hold exactly 1 liter of paint. The cost is proportional to the surface area. All that means is that the more total surface area we have, the more cost we have. As one goes up, the other goes up. That's what directly proportional means. And our task is to find the dimensions that minimize the cost to make the paint can. So we're trying to make this as cheaply as possible based on the conditions there. So we notice that our can is a cylinder. That's important at first. And I'm noticing that we have 1 liter. We have to decide what 1 liter represents. A liter is a volume measurement. And so that's just telling us how much paint we're going to have in the can. And so there's a couple of challenges with this question. One of them is with the units. They ask for dimensions, and we're being asked to turn liters into dimensions. And a liter isn't a dimension, it's a volume. Dimensions are like inches or centimeters or meters or something like that. And so we're going to need some sort of a conversion factor. And the one that I think will be most helpful is this. If we remember from our science classes that 1 liter is equivalent to 1,000 cubic centimeters. Okay, and so remembering that volume is a cylinder in this case, we're finding the volume of a cylinder, that is pi r squared times height. Okay, and that's one that we should remember from geometry class. If you don't, what this is, that's the area of the base times the height. It's kind of like area of a square, base times height, or or a cube. You're taking the area of the base times the height. So we know that needs to be 1,000 cubic centimeters. Okay, and that's going to be sort of our entry point into the problem. The other thing that we've got to think about is our optimizing equation, or it's sometimes called the objective equation. And that's the one where we decide what is our min or max. Now we're told right here that we are finding a min. So let's see what it is that I need to minimize. We were asked to minimize the cost. So the minimum cost, but we were also told that cost was directly proportional to the surface area. And so I'm not going to say equal, I'm going to say cost implies surface area, or cost therefore surface area. Surface area of this, we've got to think about the three different surfaces. There are two bases, each one is a circle, so that's 2 times pi r squared. Remember, pi r squared is area of a circle, and we have two of them, top and bottom. And then we also have the side of this. And if you don't remember, it's like a soup can label. If you take the label off a soup can, it's a rectangle. So it's base times height. But in this case, the base is going around a circle. So that's a circumference. So that's 2 pi r times height. And so this, and I'm going to bring that min over to the right, that's what we're trying to minimize. We're minimizing the surface area because minimizing the surface area will also minimize the cost. And so I'm going to take a look at that equation, and I immediately notice an issue, and that issue is right here. If everything was r, that would be fine. That would mean we only had one variable, and we know how to do derivatives with one variable. But as soon as that little h is sitting there, I have a little bit of an issue. So just like in the last two exercises, I'm going to look back up at that first equation I wrote, and I'm going to try to solve it for h so that h will die. And so here we go. Divide by pi r squared, divide by pi r squared. And so now, bada boom, bada bing, I have an equation for h. And we can just make a direct substitution down below. And now we'll have an equation that only has r in it that we know how to take a derivative of. So here we go. I'm going to rewrite this again. 2 pi r squared plus 2 pi r. We're not writing h. We're writing this. And so here goes. That's 1,000 divided by pi r squared. Before I get into taking the derivative, I want to simplify this because, sure, I could do this, but the problem is right here we have both a product and a quotient rule built in. I would rather not do both if I could avoid it. So let's avoid it. I can't simplify the left part, so that's 2 pi r squared plus, let's do some simplifying, and here's what I see. I see a pi on top and bottom, pi, go away, and I see an r and an r squared, so that simplifies out a little bit. And then we've got 2 times 1,000, that's 2,000. I'm not going to write this r down here that way because that's not as calculusable. And so I'm going to bring that up and make that an r to the negative first power, and that equals my min. And so now I have an equation that's a lot easier to take a derivative of. So let's dive right into that. And so we get 4 pi r minus, because we're bringing that minus 1 in front, and we have a plus and a minus together, minus 2,000 r to the negative second equals 0. I want to rewrite this in a way that's a little bit easier to do algebra on. So the things that are very calculable are not as algebraable. Okay, I didn't really think about that. I'm not sure that's a word. 2,000 over r squared equals 0. And from here, the algebra should be relatively straightforward. Let's move this to the right side. And so we get 4 pi r equals 2,000 over r squared. And then we're going to do a little swap here. So I'm going to bring this r squared up, and I'm going to bring this little 4 pi down. 2 for 1 special. So we get r cubed equals 2,000 over 4 pi. Continuing to simplify, 2,000 divided by 4 gives me 500 over pi. And I want to get rid of that cube, so I'm going to use a cube root. And we were asked for the dimensions, so I'm thinking that it would probably be best if we offer up an approximate value for r, and that comes out to be 5 0.42. Now, do you know what the units are on that? So remember, we were given liters. We converted that to cubic centimeters. We just took a cube root of it, so it's not cubic centimeters anymore. It is just centimeters. So that answers the question, what's the radius? But we were asked for the dimensions. So we were asked for both radius and the other dimension of a cylinder would be the height. So we need to now go back and try to figure out what the height is, keeping in mind that we found cube root of 500 over pi to be the radius. And so I've got this equation right up here. Now I'm going to drag it down the page and rewrite it because I'm feeling like I'm running out of space here. So I'm going to drag that down to the bottom. So what is that? 1,000 over pi r squared. Oop. 1,000 over pi r squared equals height. And we had an expression just a second ago for r. And so all we have to do is plug that in and off we go. So here's what that's going to look like. 1,000 divided by pi times r. Let's see what r is. That was the cubed root. Let me get rid of those dots. That was the cubed root of 500 over pi. And we're squaring that. And the reason we're squaring it is right there because it was r squared. And so all I'm going to do is I'm just going to type that in a calculator. We know that that was h. And what that comes out to is about, I should make these approximately, about 10.84 centimeters. So now we've named the radius, we've named the height, here they are, and so we've named the dimensions of our can. Okay, so this should serve as hopefully enough of an intro to where you can get into the assignment. And remember, you're going to be given the solutions with the assignment. So if you're getting stuck at all, just flip over the page and check out the solutions. In some of them, I offer you a diagram and the solution. So if you're really stuck, take a look and see what the diagram looks like. Maybe that's why you're struggling, is if you didn't draw it correctly. And I think that'll help you out. I hope you enjoyed the video and hope it was helpful. And I'll see you next time.